Good morning. So look, please, we are dealing with second formula. We did not obtain yet this formula. We will obtain it. That is 17.7, and that is when the load is applied with some eccentricity. Idea is that ideal situation is seldom realized in practice. That means that loads are not always applied centrally. They may be applied with some eccentricity, and this eccentricity is denoted by E, small e. Okay? We were solving differential equation. This differential equation, second derivative of v with respect to x plus p over ei v equals minus p over ei times e. That is this eccentricity. And what we did actually is as follows. We have a general solution that was derived before. And now we want to obtain some particular solution, any particular solution. And we said that because this is constant, P is a load, EI is a flexural rigidity, is eccentricity, this is minus sign. So this value is a constant. Because it is a constant, idea comes, let us look for VP, particular solution, as a constant. VP equals A. I substitute this A into here. A, when I differentiate A, then I get 0, 2 times or even once. So, because constant does not change, whereas derivative means slope or change. So then I substitute this here, I get P over EI A equals minus P over EI E. So I get that A equals minus E. So final solution, but with constants involved, that is V complementary plus V particular equals C1 sine square root of P over EI x plus C2 cosine of square root P over EI times x minus E. Now what we have to do is satisfy the boundary conditions. So boundary conditions are like this. So that is page 18.1. Today is lecture 18. So when x equals 0, then v is 0. So I substitute x equals 0, then sine of 0 is 0. This term is gone. C2 cosine of 0 is 1. C2 minus E equals 0. So we get C2 minus E equals 0. So then we get C2 equals E. Now, when V equals L, that is this V. When V equals L, then displacement is 0. So this gives me, look please, C1 sine P over EI L. This guy is 0. This guy equals C2 equals my E. So that is plus E cosine P over EI L minus E equals 0. So from here we get, look please, C1 sine, I will make derivations, P over EI L equals, this E goes out, E, 1 minus cosine P over EI L. So we are done with these pages. I will go back. I will just use now notation 18. So from here we get C1 equals E, 1 so that is this one. E 1 minus cosine P over EIL divided by this expression, sine P over E over EIL. So that is C1. Now we would like to simplify this expression. 1 minus cosine P over EIL, that is this numerator. Numerator's simplification. One equals, so I will take half of this argument. Then equals sine square P over EIL over 2 plus cosine square P over EIL over 2. I can actually choose any argument that I want to use, okay? That is this and that is this. Then minus cosine. Now cosine can be expressed in terms of half argument as cosine square minus sine square of half argument. So that is cosine, so that is this. Cosine square of half argument minus sine square of half argument. So then, look please, sine, cosine, and minus cosine cancel each other. And we get 2 times sine square P over EIL over 2. So that is one term. Here there are 2 terms. Now, denominator. Denominator is sine P over EIL. I'm writing it equals 2 times sine of half argument and cosine of half argument. So we get that now we divide numerator by denominator. Equals sine and 2 and 2 are canceling each other. 1 sine and with this sine cancel each other. So what is left is sine divided by cosine. And then there is, of course, E. So C1 equals E times tangent P over EI, square root, L over 2. So I got C1. So if I got C1, then I have, that is E times these tangents times sine P over EIX. This is not dependent upon x. This depends upon x because we had C1 sine x. Then plus cosine P over EIX minus 1. So that is this final expression. Due to symmetry, the maximum displacement occurs in L over 2. So that Vmax equals E tangents P over EI square root L over 2 sine P over EI L over 2. So that instead of x, I substitute L over 2. And here in cosine also instead of x, I substitute L over 2. So I will, maybe I'm hurrying, you are not sitting here, and you cannot tell me, please stop. So I'm telling myself, please stop, and allow you to write. Yes, it is correct that I will later place this on canvas, but we better not run here also too fast. So then we get E, tangent is sine over cosine, then times sine, plus cosine, minus 1. Now look please, this is a ratio. This is not a ratio. So therefore, I would like to bring it to common denominator, which is cosine square root p over ei over L2. Then will be, so I multiply this by this cosine by cosine, will be sine square plus cosine square, which equals 1. So I will have 1 over cosine minus 1. Okay? Okay, then expression for V maximum is as follows. V maximum equals E, that is eccentricity. Indeed, V maximum is proportional to eccentricity. 1 over cosine P over EI L over 2 minus 1. So this is 1 over cosine is second function, second of x. So that means that is second of P over EI. Usually in Europe we call it seconds, not second, but formula is second formula. Seconds function. So that is second formula. Not second formula. So we found that maximum displacement due to eccentricity equals second function of P over EI, L over 2 minus 1. Any questions? Please don't wait until lecture is ending. If you have any questions, send me a lecture immediately, and I will be reviewing and coming back to all of you with the question and answer. The only thing probably I will be deleting is the student's name. Okay, that means that, look please, when system is ideal, that is ideal column. That is page 684. Then behavior is like this. Until we reach P critical, there is no displacement. Nothing there. So then here there is some value. We don't know which value. Okay, that is now when epsilon, when V maximum is proportional to epsilon. So V maximum is, so that this is a behavior for some epsilon that is not 0. So V maximum is different from 0. It has some value. Okay, so that is it. Now, E, this author says, E is never 0. Okay, it says, eccentricity is never 0 due to imperfections in initial column straightness and load application. It is impossible, we say, that load is applied exactly in the center. Pay attention in statics and in strength of materials. We always considered loads are perfectly applied. We did not allow for any imperfection. Now we suddenly come in intermediate strengths of materials and tell you, world is not perfect. Okay? So, but this is a scientific case for that. World is not perfect. Wow! I mean, suddenly, strengths of materials deals with such a statement, which is, I would say, a philosophical statement. World is not perfect. What we mean is our modeling of the system is not perfect. Our modeling is not perfect. Our ability to apply load centrally is not perfect. Now, Bill Gates has, maybe you can find, Bill Gates has some statement that we will consider as strange. Life is not fair. Okay, we of course revolt against this statement, but sometimes we see that there is something that we call unfairness. So we have to deal with this, fight with this. So in this particular case, we could say, okay, apply force as centrally as possible. Yes, but maybe then we have to pay bigger price. So then we say, okay, we will design the system so that there is eccentricity, but I should know how to deal with this non-ideal situation. Okay, second thing is that this relationship is non-linear. Okay? Non-linear relationship between load and deflection. Okay, that is this load and deflection. That is P and V maximum. Pay attention, we said, look please. We said V maximum equals E, then seconds, P over EI, L over 2 minus 1. So that is not a linear relationship. There is seconds, there is a square root from P over EI, so that is not a proportional relationship. This is also for the first time in academic life. For the first time, okay, forget this life is not fair, we are not dealing with that situation, but world is not perfect, or our application, or our modeling is not perfect. Our modeling is not perfect when we talk about centrally loaded systems. For the first time in our academic life, we also see that, look please, non-linear relationship between load and deflection. We did not have it before. Okay, we go further. 18.5. So the second formula, maximum stress. Now we want to find maximum stress. In the column can be determined by realizing that it is caused by both the axial load and the moment. Moment because of eccentricity. So then maximum will be, bending moment will be P times E. And then there is also, that is this E. And that is then additional V max, V maximum. So E plus V max. V max we calculated is a function of E. Okay, so this is function of E. Of E. Then look please, Sigma maximum equals P divided by A, that is the stress because of the load. Then that is from strength of materials. Moment divided by moment of inertia times the maximum distance from out to the outer fiber. Okay, so if that is a circular cross section, then maximum stress occurs here in these fibers. Distance is C. Here there is just single fiber. Here there are many fibers in the rectangular cross section. That is a distance. Distance is C, and this fiber and this fiber, all these fibers are having the same stress. So this formula you studied in strength of materials, both of them. You studied separately. Separately, I mean you studied the expression for the stress when load is centrally applied and there is either tension or compression. And then separately you studied in bending. So now I substitute this okay, and I'm getting P over A okay, now I will P times V max. Okay, so V max will be, that is I over C comes from this form. Let me. I and C belong to the strength of materials formula. So this I and C are also here. So E times second square root P over EI L over 2 comes from this formula, second formula. Now there is also, we define radius of gyration, I over A. Okay? Then what we are writing here is as follows. P over A we take out. Then this gives me 1. Then what is left, I will write down. 18.6. Look, please. We have the second term. P is C, I, second, P over EI, L over 2. That is the second term. Now we took out P over A. We took out P over A. So what we get? P over A. Then here is 1 plus. Then I'm writing it down. There is this P, we took out, so there is no P. Then there is E, C, I, and then there should be A here, yeah, because I took out A. If I multiply back, then will be P, and A will cancel, and then there will be no A. E, C. And then second, P over EI, L over 2. Now, I over A is radius of gyration squared. R equals radius of gyration. So then we get P over A, 1 plus EC, and here is R squared. Second, P over EI, L over 2. Now this, pay attention, E is measured in meters, C is measured in meters, R is measured in meters. So therefore, EC over R squared is non-dimensional. Okay? So then what we get actually is as follows. That is this expression is C over R squared, second L over, then pay attention. Here I also have, let me write down. We have P over EI L over 2, that is an argument. Okay, then we are writing it down. This equals that equals, look please, P over EI. Where is my red pen? I will write down A. I will multiply this by A and divide by A. Okay, then I over A is R squared. So then there is L squared, L over 2. That equals P over E, this A, and that is R squared, L over 2. From this R squared we get R, and we will get, so that is L. From R squared I get R, there is 2, and then P over EA. Okay, so that is what is written there. So that is equation 1319. So the final expression is this, P over A. So that is a familiar expression. Why did we do all this algebra? Because P over A is something that talks to our mind. I think that I told you this story, and maybe I will repeat. 18.6. I was teaching statics. No, strength of materials. In 1989-1990 academic year. Student called me at midnight. That student was waiting until midnight probably. At home and asked, today we divided load P by area A to get stress sigma. Sigma equals P over A. So that is this. In the bar, there is P and there is A. And that is an area. Question. Why not divide A by P? Okay, my answer was like this. This is a valid question. If we divide A by P, the resulting quantity could be called relief or comfort, and equals A divided by P. Maybe somewhere in another planet creatures of that planet use comfort as a variable. On Earth, we say sigma must be smaller than sigma allowable. On that planet, comfort should be smaller or equal than minimum acceptable comfort. Okay? So we worked so hard So that is actually 7, and that is 8. So we worked so hard to create this P over A. And here there is this, okay, here sigma maximum is maximum elastic stress in the column, which occurs at the inner concave side of column's midpoint. The stress is compressive. P is a vertical load applied to the column. P is smaller than P critical unless E equals 0. Then P equals P critical. What is E? E is eccentricity of the load measured from the centroidal axis of the column's cross-sectional area to the line of action of P. C is a distance from centroidal axis to the outer fiber of the column where the maximum compressive stress occurs. A is a cross-sectional area of the column. L, unsupported length of the column in the plane of bending. Application is restricted to members that are pin connected. Okay, L effective equals L, or have one end free and other end fixed. E is modulus of elasticity. R is radius of gyration, where I is calculated about the centroidal or bending axis. Any question? Okay, if there is no question, then we will continue. Okay. So once the eccentricity ratio has been determined, that comes from the measurement. So this comes from the measurement. Of the due to imperfections of manufacturing. Okay? This comes both from measurement. if the value Vmax equals sigma maximum equals sigma yield, then corresponding load Py can be determined from trial and error procedure. Okay, so that is when E over C, EC over R square equals 0, that is Euler's formula. For not 0, then these are these formulas. EC over R square is 0.1, 0.5, 1, 1.5. So indeed, in our formula, we had EC over R squared. Okay, so that is this. EC over R squared. That is a parameter. Okay, EC over R squared. Okay, I will go now to what I promised you, and that is solution of the homework problem. 1810. I promised you, I, by the way, did not check whether you, and I don't know therefore whether students did correctly or not this problem, but I will check, and what you are going to get from me is everyone who sent me an email will receive a short notice like this in homework 18 and other homeworks, other future homeworks. I will send back reply with short comment on your solution and the grade, and we'll record the grade. Okay, so that is 1811. Okay, so I have first part, EI, second part, S plus 1 EI. Why did I choose S plus 1? I could have chosen SEI, but first student then would have uniform column, and I did not want student number 1 to have an uniform column. Therefore, I chose S plus 1. So if some student is number 36, here will be 36 plus 1, which is 37 EI. And student number 1 would get 1 plus 1 equals 2 times EI. So every student got an inhomogeneous column. No, non-uniform column. Stepped column. Okay, I did write specifically what you should do. I did write, please write differential equation for first part and then write for the second part. So, for the first part, EI V1 second derivative plus PV1 equals 0. Part 2, S plus 1 EI, V2 second derivative plus PV2 equals 0. So in the second part, then I can divide everything by S plus 1. Divide everything by S plus 1 EI. We get V2 double prime plus P S plus 1 EI V2 equals 0. I denote this as k squared. So I get P over S plus 1 EI equals k squared. Then here P over EI will be S plus 1, P over EI will be S plus 1 k squared. So in part 1 then I have, part 1, S plus 1 k squared V1. Here V2 equals V2 double prime plus k squared V2 equals 0. Okay, I think that I decided to choose some S because I don't want to, first of all, I recommended you not to carry S. I chose here some specific value of S and recommended you to do so too. So I will choose therefore, because S to carry S plus 1 is cumbersome. Okay, so that is 1812. Let us choose some specific value of S, exactly as students should do. I chose value S equals 3. Okay? Why? Why did I choose? Because 1, 2, 3, that is what I decided. Then we get, here is EI, here is 4 EI. So that is good actually. What I'm talking to you is for student number 3, this is a solution of his problem or her problem. I don't know who this problem is. So first part then is, so that is how we should have started. EI V1 double prime plus PV1 equals 0. 4 EI here. Part 2. PV2 equals 0. So solution in the first part will be some actually that is the solution of the second part. Then in the first part will be P over EI. Oh, sorry, I denoted, I did not pay attention. I denoted P over 4 EI equals k squared. Okay, if that is the case, then please here we will have first, we will write it down. 1813. So we have first part, part 1. X from 0 to L over 2. EI V1 double prime plus PV1 equals 0. We have V1 double prime plus P over EI. V1 equals 0. So, but we have k squared equals P over 4 EI. But I have here P over EI. P over EI equals 4k squared. Okay? So then we have, look please, V1 double prime plus P over EI equals 4k squared V1 equals 0. So the solution here equals sine C1 sine 2kx plus C2 cosine 2kx equals 0. In the second part, so that is x between 0 to L over 2. Okay? So I just will write it down. V1 equals C1 sine 2kx plus C2 cosine 2kx. So boundary conditions, V at 0 equals 0. So C1, I substitute this is 0, so I get C2 equals 0. Because I get C2 times 1 equals 0. So C2 is 0. Now I have continuity condition. V1 at L over 2, that is here. Here. Equals V2 L over 2. And also derivatives. V1 prime L over 2 equals V2 prime L over 2. Indeed, 1815. Okay, this beam, okay, this is a beam, and that is a beam. So here we cannot have, let us say, this displaced like this, but this displaced like that. Otherwise, that means that that is a collapse. Displacements must be 0. Must equal V at V1 L over 2 must equal V2 L over 2. Also, we cannot have this. And we already discussed this in beam displacement problems. We cannot have also, let us say, this here and that there. We cannot have slope discontinuity. Okay, so this slope is here like this, and there is like this, so different slopes. We cannot have different slopes. Beam will not do this. Voluntarily, so to say. Okay, so then we get, look please, C1 sine 2k L over 2 equals, and C2 is 0, plus C3 sine k L over 2 plus C4 cosine k L over 2. Now derivative. First derivative of this, 2k C1 cosine 2k L over 2 equals derivative of this, C3k cosine k L over 2. And from here, cosine will be minus sine. Minus C4k sine k L over 2. At x equals 0, we should have boundary condition. That is, displacement is 0. C3 sine kl plus C4 cosine kl equals 0. So we have the following three constants, C1, C3, C4. So I'm writing down this C1, the constants. Coefficient matrix instead of in front of C1 is sine 2k over L over 2 will be KL, K times L. In front of this, I have to transfer to the left-hand side. So will be minus sine KL over 2. Here, minus cosine KL over 2. Here, C1, 2k cosine 2k over L over 2 is KL, minus k cosine KL over 2, plus k sine kl over 2. Now here, there is no C1, so C1 is multiplied by 0, C3 by sine kl, C4 by cosine kl. So I get this expression, 3 by 3, this 3 by 3 determinant must be 0. I will wait a minute so that you could write it down. Now, I'm opening this, and I will get, look please. This times this times this. Sine KL minus K, but I cancel by K. Minus cosine KL, cosine KL. Is 0, is here. Then this times this times this is 0. Then this times this times this is 2 cosine KL sine KL minus cosine KL 2. Then these terms, product of this is 0. And this times this times this. Sine minus sine KL, sine KL, sine KL over 2. Then this times this with minus will be plus sine KL over 2 cosine 2 cosine KL, cosine KL. Then we need to know algebra, of course, otherwise we will make a mistake. And at the end, what we get is some expression, but sine KL over 2 comes out. In your particular case, it depends on the number. Maybe it will come out, maybe not. We don't know. Sine KL over 2 comes out. So then what is left? So we get, I have to number the pages. 18, 14, 15. Eighteen, 16 here. And then it is 18, 17. So we get two possibilities. Sine KL over 2 equals 0, or tangents KL over 2 squared equals 2. Okay, in your particular case, whatever you get, you have to just, I will show you. I will show you in this case. If you succeeded to get sine KL over 2, then, okay, that is one solution, that is second solution. First solution. Sine KL over 2 means KL over 2 equals pi. So from here we get K. K equals 2 pi over L. What is K? We denote it. That was our notation. P over 4EI. That equals 2 pi over L. So from here we get P. I square this and square this. We get 2 pi over L squared and times 4EI. So that is 2 squared is 4, times 4 is 16. 16 pi square EI over L squared. This cannot be, because look please. Why did I write this cannot be? 18, 17. I have this beam. That is EI. That is 4EI. So P critical. So if beam is uniform with rigidity, with flexural rigidity, EI, then P critical equals pi square EI over L square. Okay, that is for this beam. EI. Or that is this one. If beam is uniform with flexural rigidity. For EI. So that means that beam is like this. Then P critical equals pi square 4 EI over L square. That means that for this beam, for our original beam, which is stepped, P critical must be between these two values, pi square EI over L square and 4 EI pi square over L square. But we obtained 16 pi square. We obtained 16 pi square, so that is outside this range. So this cannot be. So what can be is for 1818. That second possibility. That means that tangent scale over 2 squared equals 2, or tangent scale over 2 equals square root of 2. So that is 1819. Okay, so then I'm depicting, and if you have a bigger expression, then you have to depict. So that is this tangents. I'm depicting tangent scale over 2. That is function 1. Look, please. I have this. So I'm calling this f1 of KL over 2. This is f2 KL over 2. This is KL over 2. So that is a function 1. And second is a constant. That is square root of 2, or approximately 141. So the intersection is here. They should be found on computer naturally, this value of intersection. Anyways, from this figure, I see that this value is less than, this is pi over 2, which is 157. Okay, you can find on computer, this will be 0.955. Okay? These are the functions, f1 and f2. So, KL over 2 equals 0.955. From here, I got P critical equals 14.6 EI over L squared. So it's not the value more than pi square EI over L squared and less than 4 pi squared. 4 pi squared will be 40. Here is 14.6, not 40. Makes sense. Okay, 14.6 is bigger than approximately 10 and smaller than approximately 40. So that makes sense. Look, that is how your boss will check whether your solution is correct or not. He will roughly approximate the problem, and he will say, okay, solution should be somewhere in between. But please don't say that that is 10 plus 40 divided by 2, which will be 10 plus 40 is 50 divided by 2 is 25. 25 is far away from 14.6. And 25 is not in the, not error for safety. Because you think it will buckle at 25, but In reality, it will buckle at much lower load, 14.6, or approximately 15, rather than 25. Also, geometric average does not work. 10 times 40 is 400. Then square root of 400 is 20, which is closer than this, but still it is bigger than 20. So, what you have to do then, 1821. Get the determinant, you had to do determinant 3 by 3. Then you get function of KL, or function of KL over 2. And then you have to depict this function. Okay? That will be the root. Okay? This when it intersects is 0. That is a graphical solution. That is F, that is KL or KL over 2. Now just one more question, and that will be in project. Okay, first of all, projects. The time for submitting the project, I think, was March 19, if I'm not mistaken. March 19 has passed already several days. Please submit project as soon as possible. Yes, I made the submission time on 31, but don't wait till 31, because we have a test on that day. Please submit this project as soon as possible. Please submit today. Please, that is a request. Please submit as soon as possible. Okay, again, you will get back from me electronic mail saying my comments and grade. Email, my comments and grade. Okay? I will prepare second project as soon as possible. Second project is on buckling of structures. Now, pay attention, just some comments. There will be problems like this. For example, clamped, simply subclamped and free, for example. And this is, let us say 7 EI, and that is EI. And that is a load P. That will be in the project, one of the. So, in cases different from simply supported column, we must use fourth order differential equation. Okay? Not second order. Second order ordinary differential equation is customary to be used for simply supported columns. Any questions? So I addressed the questions that students have, not one, but especially one, who wanted me to post the solution. That is why I'm not posting the solution usually, because there are many subtle points, and pay attention, the course does not equal the problems. Problem is just one of the problems. Just because you know how to solve the problem, as I explained, does not mean that you know the course. And it does not mean that by solving problems then you know the course. What we have to do is to study the theory. Without studying theory, there is no way of conquering the course. Yeah, I think that there was this famous German scientist, 1823, Boltzmann. Theory is the most practical thing. Okay, so that is his expression about importance of theory. Because theory and practice are not disconnected. Okay. Any questions? Okay, if there are no questions, then I will continue with an example. Look, please. This appears, that is the second formula, appears on page 687 of our book. I'm trying to use our book as much as possible for your convenience. As you know, this book is available on Google free of charge, this edition, that we got 9th edition. The W8 times 40, A992 steel column is shown here on 1317A, fixed at its base and braced on the top. Okay, so you see that that is an IB. Okay, so that it is fixed from displacement. Again, here it is fixed from displacement, yet free to rotate. So it can sway to the side in the ZY plane. That is a plane, so it can slide. Determine the maximum eccentric. Look, please, this load is not applied centrally here. Why? Oh, because, pay attention, loads come from environment. Loads come from environment. The environment does not take my course or Euler's course. Environment is acting as it's acting. So environment, as it were, did not know that it should be acting here. It acts here. Now, my problem as an engineer is to deal with the problem if P is in the center, or to deal with the problem when it is not in the center. Whether it is eccentric, or with eccentricity, or without eccentricity. I must be, like a medical doctor, I must be able to treat a patient in any condition. not just in one specific condition. I cannot say I'm a doctor only of right foot, say. I hope that there is no such a thing as doctor of right foot only. From the support condition, it is seen that about y-axis, the column behaves as it were pinned on the top and fixed on the bottom. So it's simply supported here and fixed on the bottom and subjected to axial load P. That is like this. About the x-axis, the column is free at the top and fixed in the bottom and is subjected to both axial load and moment. P times E, 9 inches. E equals 9 inches here. Look, please, that is a centroid, so that is centroid. From centroid, distance is 9 inches. So small e is 9 inches. So P and moment, P times 9 inches. Okay, y-axis buckling. Buckling with respect to y-axis. Effective Long's factor equals 0.7 because it's clamped, simply supported. So KLY equals 0.7. This is 12 inches, 8.40 feet, or 100.8 inches. Using table in Appendix B to determine IY for W8 times 40 section, we get this E equals 29 times 10 in power 3 KSI, and that is E. That is EY, 49.1. So we get 1,383. Okay, that is P critical in Y direction with respect to y-axis. Now x-axis yielding, that is this axis. So kx equals 2, clamped free. So klx equals 2 times 12, 24 feet, 288 inches. Again, using the table and determining A equals cross-sectional area 11.7 inches squared. C equals, so what is C? C equals that is C. C. 8.25 inches over 2, that is whole length divided by 2. And therefore, radius of inertia, or radius of gyration, equals square root I over A equals 3.53 inches. So second formula, Px over A, 1 plus EC over R squared. That is, we obtained today. That is this factor. Then seconds function, KLX, 2RX, P, EA. So what we get actually is as follows. Yield stress then equals 585. Px, 1 plus 2, 979, second of Px. Now we have to solve it by trial and error. One may say, oh, first solution, what is this trial and error? What will be the first solution to take? Okay, first solution to take will be, imagine that we throw this away, we get px. Px equals 585. Then I substitute 585 here. Okay, so for example, I will rewrite this formula like this. Px equals 585 divided by 1 plus 2, 979, second 007 px. So first I substitute this is 0. Then I get 585. Then I substitute 585 here. Then it will be 585 divided by all this expression will be second approximation. Then I substitute again, and I get 115 kips. Please check this well.